Okay, we're recording here. Uh, yeah. Okay, we're recording video 27. This is an easy video. It really is. Not much going on here. I'm going to make it up to you in videos, probably 28, 29, and 30. But this is, nevertheless, it's important. Obviously, or I wouldn't be covering it, but it's, well, it's what it is, okay? So what I want to do in this video is talk about some concepts, some topics, R squared and R. We refer to R squared as the coefficient of determination, R as the correlation coefficient. And when I think of these more in terms of descriptive statistics. And descriptive statistics means that we're just trying to describe the data that we've collected. Inferential statistics, as I hope you know by now, we're trying to generalize to something bigger. Inferential statistics, we think about for a simple linear regression model, we have parameters beta 0, beta 1, and sigma squared, and we find estimates of those from our sample. Descriptive statistics is not seeking to do that. Descriptive statistics is seeking to just describe the data that we have in front of us. Now, it's kind of interesting. I'm going to get on a little bit of a tangent here. Let me show you something that where you see misuses of this all the time in statistics. And let me bring up Google here. There's one out there that I poke fun of all the time. It's called the Rasmussen reports, and they do a daily tracking daily presidential tracking poll. And probably nowhere are you going to find a misuse of statistics like, well, I don't know. I rarely find any statistics in the media that is reported correctly, but this one's one that is easy to find, and well, come on. Well, not really sure why this isn't coming up. Maybe. Okay, here we go. Now, this is a semi-interesting uh, tracking poll, and before we have any of you who are just Obama haters or um, no, thank you. Okay. Um, uh, no, I'm not a spokesman for Kroger or Expedia or Facebook or Twitter. But what I want you to look at here is a statement that they make every single day that's not true. Okay, and again, I'm going to look at Obama's presidential job approval index, and for those of you that aren't big fans of Obama, I'm not picking on him. This chart right here. Uh, I can go back in time and show you that it looked the same for, um, goodness gracious, this thing is running slow today. It looked the same for Bush Senior, Clinton. Seems like we start out where the green, which is the approval, the strong approval, is higher than the red. Pretty soon the lines cross, and then pretty soon the red is on top of the green. Now this is kind of unique right out here. I have to admit, I haven't looked at this recently, but Obama must have done something really nice in February, at least because the lines actually come back and actually touch. So I've never seen that before. But anyway, what I want to show you here is the very first sentence, how they mess up descriptive statistics and inferential statistics. And it says right off the bat, the Rasmussen Report daily presidential tracking poll for Tuesday shows the 47% of likely U.S. voters approve of the President Obama's job performance. Well, no, it doesn't. What they do here, Rasmussen takes what's called a 3-day rolling average of 500 people per day. So the day that I'm actually putting this video up is on a Tuesday. So the 1,500 sample that they're examining today is from the 500 from today, Tuesday, yesterday, Monday, and the day before, Sunday. Tomorrow, they'll use, again, the rolling 3-day 500 or 1,500 total. They'll use the 500 from Wednesday, the 500 from Tuesday, and the 500 um, uh, from Monday. So they use the last 3 days as a rolling average. Um, well, what they do here is they're assuming something in statistics that can't be assumed, and they're assuming that their sample is perfectly representative of the population for which they're trying to generalize. So again, 47% of likely voters. Well, that's not what we can say here. That's not what they can say. What they can say is that 40% of the 1,500 who were sampled. Now that's a descriptive statement, and that's perfectly legal in the context of what they're doing here. But when you start generalizing to this, to the, to all likely U.S. voters, they're making a statement that they can't say. Now, luckily for them, they won't have stat geeks like me on their tail. What they actually do is they actually come down in the last paragraph, in the last sentence. Statistically, you can show that about 1 in about 500 people, oddly, are actually going to read this. Most people are going to read the first sentence and they're going to stop. But if they come down to the last sentence, they actually do cover their butt and say that the margin of sampling error, and this is where I am right here, for the full sample, 1,500 likely voters is plus or minus 3 percentage points with a 95% level of confidence. So what they can say with statistical accuracy with a margin of error plus or minus 3 is there's a 0.95 probability. Let's do the mental math. 47 minus 3, 44. 47 plus 3, 50. So there's a 0.95 probability this interval, 44%, 50%, contains the percentage of all likely U.S. voters who approve of the job performance that Obama is currently doing. Same thing with the 51%. We can't say 51% of all likely U.S. voters disapprove. We can say that there's a 0.95 probability that 48% to 54% contains. So and it's kind of weird. You hear these guys referenced all the time on the nightly news, and they're just doing it wrong. They're misguiding people. They're assuming that their sample of 1,500 is perfectly representative of the population for which they're trying to generalize to. So I'm going to shut this down and get off my little soapbox on this, okay? And what I want to do here is talk a little bit more about, when descriptive statistics is enough. Guys, pretty soon you're going to complete this class, and everyone is going to have a score on the midterm and a score on the final. Now, hopefully, we've got, really, really, really high scores. So, but nevertheless, if I'm seeking to examine these scores, look at the relationship between the midterm and the final, specifically looking at how midterm predicts final score, I may be interested in doing that. It's certainly a worthwhile task to take on. But I haven't got anyone to generalize to. I have 10 students here. I'm seeking to examine the relationship between midterm and final for 10 students, you guys, but I'm not seeking to generalize to anyone. So in that capacity, describing the relationship is as far as I want to go. Now, I'm not seeking to take this line and predict anyone's final from their midterm. If an 11th student comes in after the midterm, I'm sorry, we have an 11th student who actually takes the midterm, but for some reason doesn't show up for the final, I'm not going to take their midterm and predict their final here. I'm not going to do that. I'm just seeking to examine the relationship and to, further explain it. Okay. So, guys, the goal here again with R and R squared, our goal is simply to assess the degree of the relationship between X and Y. Guys, I'm going to do that with R squared, which we call the coefficient of determination. There's probably no single measure that's dependent on more than R squared. It's gonna be around for a long time, and I'm sure you guys probably know this, that R is our correlation coefficient. So by the time this video's over and done with, you're probably going to know far more about R squared and R than you ever thought possible. All right, guys, let's just revisit some basic things. I'll put basic in parentheses because, So revisiting some basic topics and ideas. Our sum of squares for our total. And if you remember, we find that by something, seems like the dogs always want to bark when I get on here to a presentation. All right, anyway, guys, our sum of squares for the total is the vertical distances from our observed y's to the mean. And what I want you to notice here is x is not involved in this calculation. Something else we looked at was the sum of squares for the error. And certainly x is involved because it was used in that calculation. Now, where we want to go from here is actually kind of cool, I think. What we can say here, let me get kind of an idea of what we're doing. Okay, so so what we can do from here is we can reduce let's just call it the uncertainty in predicting y by examining the difference here. We know the sum of squares for the total minus the sum of squares for the error is the sum of squares for the regression. And what we can furthermore do is we can look at a proportion of these sum of squares to the total variation. So if we examine this, if we look at the sum of squares for regression over the sum of squares for the total, we're ultimately examining the proportions of total variation. So of the total variation, what proportion of that is explained by our sum of squares on the regression? Sum of squares on the total doesn't account for x. Sum of squares on the regression obviously accounts for x. And we can examine that variation, that ratio of the variations to actually come up with R. So, guys, technically R is the sum of squares for our regression over the sum of squares for our total. And another way of looking at that is that R squared, obviously, is just equal to 1 minus the sum of squares for the error over the sum of squares for the total. So we sort of say, well, 100% of our variation is explained if we come in and subtract out the proportion of variation of the error to the total, which is precisely saying that we're looking at the proportion of the variation through our regression over, well, to the sum of squares for our total, the difference between the y's and the y bars. Now, interesting concept here, I think. We know that the sum of squares for the error has to be less than or equal to, and typically sum of squares for error is going to be less than our sum of squares for our total. The only time it's going to be the same is when let's see, the only time that those will be the same is when the sum of squares for regression is equal to 0, which could only happen when there's no linear association. So, but anyway, what we could do here is we can see that the sum of, we can divide through everything by the sum of squares for the total. And then we're going to get this. Now, the sum of squares for the total, I'm sorry, the sum of squares for the error divided by the sum of squares for the total. If we look at this, it should be pretty easy to see, examine this line right here, that the sum of squares for the error, sum of squares for the total, could be rewritten as 1 minus r squared. Now, what I'd like to do now is subtract 1 from everything. And then I'd like to multiply through by -1 for obvious reasons. And then I'm going to get 1 to 0. Now, typically, guys, I know this is really hard to get our beginning algebra students, although I never teach that class, but to get them to see that writing in terms of the lowest term on the left is much more convenient. So, guys, we see that the values that r squared take on are between 0 and 1. And guys, at the end of the day, the larger our r squared is, we can say, let's see how I want to put this. The larger r squared, we can say that more of the total variation in y is explained by introducing x. Now I'm being very, very, very careful here because I know what's coming up. Now, ultimately, what we'll want to do is we're going to do some hierarchical modeling to where we have multiple regression setting. And we're going to, for example, want to bring extra predictors in, and we'll examine the change in R-squared. So I'm trying to create something here that's far more general for the goal of the class. Now, guys, I think it kind of helps to understand the bounds, or at least to examine the bounds. Although R-squared is rarely, in practice, 0 or 1, I think it's going to help here to examine, exactly what is going on when R-squared is equal to 1 and what happens when R-squared is equal to 0. Well, guys, R-squared equal 1 is the simplest case, and that just says that our data all lies on our line of regression. So in other words, x accounts for the total variation in y. On the other hand, a situation where R-squared is equal to 0 could only happen when our data is on a horizontal line. In other words, our slope is 0. So in this, x is absolutely no help, no assistance whatsoever, because y is always going to be a particular value. Now, again, in practice, you're not going to see that. You're going to see somewhere, in practice, you're going to see that R-squared is, much more typically between 0 and 1. And you also see in practice that R-squared is usually presented as a percentage, because it's precisely how we define R-squared when we look at our interpretations. So I think what I want to do now is just no, I don't know. I'll tell you what. Let's get out of here and get into R. And just remember that there are data sets that we can use. I'm going to go library mass, because that's a data set that contains some pretty cool stuff that I've looked at before. I'm sure there are others. There are probably others that I haven't looked at that contain cooler stuff, but this is one that I'm familiar with. If we go data, open parentheses, close parentheses, we'll see that we have different things, different data sets. And I don't know, this cars kind of jumps out at me today, the speed and stopping distance of cars. I don't know, that may be something that'd be kind of cool to look at. So let's go data, cars. And then we can do names, cars. And we have speed and distance. Well, it may be interesting in the simple linear regression setting to examine the stopping distance as a function of speed. I don't know, maybe not. Okay, so just to show you what we have to do next, notice if I go mean of speed, I'm going to get an error. The reason is I haven't attached the data yet. So guys, always attach your data. And I can look at mean of speed, which is 15.4. I really don't know what that's measured in. Okay, and I can go mean of distance, and it looks like maybe 42.98 feet. Now, if I want to examine the model, what I would do here is I would go model, linear model, and I would want to predict distance from speed. Guys, when I type model, what I do is I get my coefficients for my model. You know, at our stage of the game here, where we're trying to learn bigger, better stuff, okay, that's fine. But that's certainly just the tip of the iceberg of what we're trying to do here. Next thing I may want to do is do a summary of our model. What this is going to do is going to give me an expansion on the inferential analysis of our coefficients. It doesn't give us anything in terms of sum of squares for our sum of squares, mean squares, degrees of freedom. It gives us nothing other than that. But if you notice, it does give us our what we call our multiple R squared. Now let me explain the difference between multiple R squared and adjusted R squared. Multiple R squared is extremely useful when we have one predictor. The adjusted R squared, we can show that the adjusted R squared is a biased estimator. And what happens once we get into multiple regression, the multiple R squared is actually always going to be an overestimate when we have two or more predictors. So the correction factor is the adjusted R squared. So guys, we're typically going to look at this value when we have two or more predictors, but we're going to look at this value when we have one predictor. Okay? So what I would say here is, you know, our R squared is 0.6511, which indicates that 65.11% of the variation in, what are we doing here? Speed, no, distance, is explained by the regression on speed. So why does distance vary? Well, it does. And about 65% of that variation in distance, our y, can be explained by the sum squares, well, by the regression on speed. Okay? So, you know, easy to do. Now, sometimes you're only going to be given your ANOVA. So if we look at our ANOVA for a linear model for model here, then we're going to get into sum squares, mean squares, and so on and so forth. I want you to be aware that in given this situation, notice that R squared is going to be calculated by taking, this is always the sum of squares for the regression. And remember, the sum of squares for the total is the sum of the it's the addition of the sum of squares for our regression and the sum of squares for our error. So guys, here the sum of squares for our total is going to be equal to 21186 plus 11354. So our sum of squares total is 32540. So we can say that our R squared, I don't know if it'll let me do this or not, is going to be the 21186 divided by sum of squares for our total. Yeah, it's not going to let me do that. So let's call it R squared. So this is going to be 21186, which is the sum of squares for our regression divided by the sum of squares total. And we can see that R squared is 0.651, which is exactly what we got before. So R squared is really, really easy to find. It's my feeling that it's really easy to interpret, to conceptualize. You know, but we're going to find out later it certainly has its limitations. Now, let's see what I want to do next. I tell you what, let's just talk a little bit about limitations. Okay, so first of all, guys, in a nutshell, no single measure tells the whole story. Sorry, I know the capital's coming across as screaming, and I'm not, obviously, but no single measure does it all. Because I tell you, there's probably nothing that is used and reported more widely than R-squared, especially when we get into looking at examining other models. Now, let's just first of all talk about some limitations on R-squared before we start going hog crazy and thinking, oh man, this R-squared is the greatest thing since sliced bread in linear regression. It does have problems, okay? For example, we may say that a high R-squared indicates that we can use our model for useful predictions. Well, this is actually false. And I think okay, let's do this. I'll tell you what, let's go back. I've got to hear my calculator. Let's go back to the ACT GPA example. So, guys, ACT, we had 18, 22, 25, 28, and 32. And we had GPA as 2.4, 2.2, 2.8, 2.9, and 3.5. Well, that's just lovely. Yeah, let's do that again. 2.4, 2.2, 2.8, 2.9, and 3.5. All right. Now, I'm going to call this model 1, say. And we could run our linear model as we've done numerous times before. And what I want to do is go ahead and look at the good stuff. So, linear model for model 1. All right, so we're going to get our sum of squares, mean squares, and so on and so forth. Now, our R-squared here is going to be 0.82793 divided by 0.82793 divided by 0.18407. Well, that's just wrong. Probably asking me why am I changing everything, because I'm being a bonehead. All right, guys, obviously that's the difference here. So our R-squared is 81.8%. which indicates that 81.8% of the variance in GPA is explained by the regression on ACT. Yeah, 81.8%. If I'm publishing something and I have an R-squared of 81.8%, I'll be high-fiving. Because, that's a large value. However, let's examine the prediction interval for, whatever, an ACT equal to 32. We have friends that have a daughter who's a senior in high school, and she's taken the ACT over and over and over again, seeking for this ACT of 32, because apparently where she wants to apply, there's more scholarships available if she can get the threshold. So that's kind of why I'm just thinking about ACT at 32. So the reason what we would do here is I would go predict using model 1. I think that's what we called it, right? Yeah. And I'm going to have to do here data frame ACT equal 32. And then I want to do an interval prediction. Predict, right? Yeah. So when I do that, you can see that our predicted GPA for the student with ACT of 32 is 3.35, but we know because of sampling variation that we have to express this prediction in terms of a confidence interval. So what we can say, a 0.95 probability that the interval 2.35 to 4.36 contains the predicted GPA for an ACT of 32. Well, I don't know about you, but predicting something that has a margin of error in GPA of slightly one unit, right? So our total distance here from the 2.35 to 4.36 is 2.01 divided by 2 gives us a, I don't know, if I were wanting to predict someone's college GPA based on ACT, I would want something with less margin of error than this. Now, certainly this is accounted for by the small sample size that we have. We only have, what, 6 data size of 5 or 6, I forget. So that's certainly here. But the point I'm trying to make is just in isolation of that, the 81.8% for R-squared certainly doesn't lead us to where we can be able to make useful predictions. Another thing that so another issue that we may want to look at is that a high R-squared indicates that our regression model is appropriate. In a way you might think of that, or, a good fit. Well, again, when this comes under investigation, we find out that this is false, and this is really easy to illustrate. So let's just let X be the following data. So let's go 1, 1, 3, 4, and let's let Y be 1, 1, 3, 6. Now, if we examine this, if we examine the plot of x, y, we're going to see that, well, what are we going to see? Why aren't we seeing all of our data? Actually, what I want to do here, actually I want this. Yeah, let's do this. So we'll look at that. Now we can clearly see when we look at our data that a straight line relationship, it's going to fit the bill. It's going to do okay. But a curve, nonlinear model would clearly give us a better fit here. But nevertheless, let's go ahead and look at the R squared here. So I'm going to just go ahead and combine some stuff here. So if I look at ANOVA of our linear model, which is y predicted by x, we're going to get an R squared that's pretty darn high. So we're going to get 14.45 divided by 14.45 plus 2.3. So we get an R square of 86.3%. So 86.3% of the variation in our y is explained by x. But it's easy to see that, at least in my opinion, that from the plot that we would have a horrible, I think our model would be horrible here because a nonlinear model would be certainly more appropriate. So, guys, let's move on into the final topic, and this is going to be the correlation coefficient. One of the great statisticians ever, in my opinion, Tukey, said it at the end of one of his publications. He was actually, I think it was in one of his books. Now that I think about it, he talked about correlation coefficient. He said, "What do you really know from the correlation coefficient?" And he said something to the effect, "Using the correlation coefficient to analyze data is just about as effective as not examining the data at all. It is subject to so many factors. Nevertheless, let's talk about it briefly. Guys, our R value is just the positive or negative of the square root of R squared. The range on R for positive, or for obvious reasons, considering this, is from -1 to +1. So guys, at the end of the day, R is just simply the square root of R squared. So, how do you determine whether you have a positive or negative? If I have an R value, for example, if I have an R value of, 0.81. So R is going to be the plus minus of 0.81. And so this will give us plus or minus 0.9. So which one is it? Well, what you would do here is you would examine the sign of our slope. So obviously, if the sign is greater than 0, then we have data that has what I would call a positive tendency. So our R value would be positive. However, if we have a B value that's negative, then we must be fitting data with a negative tendency. So the R value that we get is clearly negative. So not rocket science here, guys. It's just use a little bit of good old common sense and realize that the R value, indicates in a way strength and direction. Um, so if we have tendency of a negative relationship, then clearly R is going to be uh, negative. So, guys, that's about really all I've got. Just some parting comments, and don't leave me yet because these are pretty important parting comments. A couple of things I would say in the end. One thing I'd like to point out here is the variation in Y. Shoot, the variation in X affects our R squared. Now, one part's unaffected. Sum of squares for the error is unaffected. As guys, think about it. What's the sum of squares for the error? Actually, it's just if we look at our levels x1, x whatever it may be, it doesn't matter whether our x's are spread out or not. This variation is the same. Makes no difference. And we always make the assumption that we have constant variance. However, the other part of it, the sum of squares for the total, is affected. So let's think about this. Let's say we have very little variation in x, from x1 to x2. Now the sum of squares of the total uses the mean of the y's. Notice we're not going to have a lot of variation here because there's not a lot of variation from x1 to x2. However, if we examine, and guys, again, we're assuming here that beta 1 is not equal to 0, obviously. So if we have x3 here creating more variation, obviously in the situation where beta 1 is not equal to 0, our y max will create a bigger range and a larger value of y bar. So, consequently, our sum of squares for total, which is just the y value minus the y bar, the sum of these squared, is naturally going to be higher. Sometimes we talk about truncating our data, which is kind of restricting the variance on the predictors. Well, that creates certain statistical dilemmas. Actually, that was part of my PhD dissertation, which is kind of cool. One other thing, really important, remember regression is not causation. That's not what we're seeking to do here. So, guys, don't take the explained. There's an I in there, trust me, literally. What we're doing here is, guys, we're just examining the relationship. Simply put. So looking at the relationship doesn't mean that that we have any sort of causation. Something I usually do in a classroom is to illustrate this is I'll go over to the wall and I'll flip the light switch, and I'll just keep flipping it on and off, and I'll ask my students, is flipping this light switch causing the light to go on and off? And of course, they're going to say yes. And I'm saying, so you're telling me that flipping the light switch causes the bulb to go on and off. Well, absolutely. Every time you flip it, it goes off. Every time you flip it again, it goes on. Well, then what I do is out of my bag of tricks, out of my bag of tricks, I'll pull out a light switch, give it to one student. I'll give a light bulb to another student, have them hold the light bulb. I'll have the other student flip the switch. And, you know, well, things are going to get really scary if that light bulb does go on, but we know it's not going to because when we get into modeling causation, first of all, there's no statistical process that proves causation. We can model it using certain techniques, which we actually will get into in future statistics classes, not this one. So there's ways that we can model causation, but we can never prove causation. So you know, guys, we're not doing anything here. Another thing, you know, finally, kind of the last parting word, R² and R are descriptive. Well, that may be the ugliest descriptive in the history of writing. Are descriptive statistics. They make statements about our data with no intent to generalize. The parameters of our model, as we have looked at it so far, there's 3 of them. Our intercept, our slope, and our variance. R² and R, although we actually will use this in inference in future stuff in this class, right now the only parameters that we are you know, interested in generalized to are beta 0, beta 1, and sigma squared. So guys, that ends the lecture. I'm glad to have this one behind me. The next couple lectures are super cool in my opinion. So so guys, that's I guess the end of video I forget 27, I believe it was. So guys, have a good one.